This, the guy I'm going, you know K and N? K nearest neighbor classification? As usual, the machine learning people know. Okay, I'm here for everybody, so. For you, it will be going over this again. For others, it will be hearing this for the first time. So, what is K nearest neighbor classification? Actually, it's a very effective way to classify. It is one of the most, or the best known algorithms for classification, and it is very good at classifying documents. I mean, it is at least, typically, it is at least comparable with naive Bayes. Very often it performs better. Not always. Very often. We will try to understand when it may perform better, when it may perform worse as well, okay? So, how does it work? It's actually very simple. You have a training set as usual. What is your training phase? Nothing. That's beautiful. Yeah, no training phase. Actually, your training phase is implicit. Okay, you have the set of training documents. Very often, the bigger the better. Of course, you know the labels of the documents. You know which class every document belongs to. Okay, that is your training set. Then you have a new document. Let me see if I have a picture. Yeah. So you have a collection of documents. Again, here you have different colors represented by these curves. Notice that you have curves here. And then you're given a new point, and what do? You look at your neighborhood, and you wonder, which are my closest neighbors? Let's, for example, say, consider one nearest neighbor to begin with. K stands for the number of points of your closest neighbors you consider. Let's say that I pick one neighbor. So it means the following. I just look up what is my nearest neighbor. Let's say, well, let's say it is this point. Okay, I don't know if that's correct, but let's say it is this point. Then I would say, okay, what is the class of this point? C, fine. This is also of class C. That's nearest neighbor. Very often, what happens is that if you just pick one document, what can happen is that perhaps you have just one document that is a bit noisy. Your nearest neighbor is maybe an outlier with respect to the class, and your classification will not be, I mean, your accuracy will not be very high. So what you do typically is that you consider more neighbors. For example, you take 5 neighbors. You pick your 5 closest neighbors, and then, for example, you will assign your point to the majority class. Let me give you an example. So let's say that, for example, now I am simplifying a little bit. Assume that again I have stars and circles. Let's say that I pick 3 nearest neighbors. Okay? Then if I pick 3 nearest neighbor, then my nearest neighbor, let's say, is this. Then the second nearest neighbor is this. The third nearest neighbor is this. Okay? Let's say that this is class C. This is class C and this is class C negated. Okay? Then I will have, for my point, I will have 3 labels. C, C, C negated. So So, how can I decide? A very simple strategy, pick the majority label. So I have two labels, C, one label C bar. My class is C, okay? This is one first rule you can apply. But you can apply different rules. For example, what you could do actually is to take, since all the points you have a unitary length, right? You can equivalently consider Euclidean distance or cosine similarity. What you can also do is just you consider the cosine similarity. You take your nearest neighbors in terms of cosine similarity, which will be your nearest neighbors in terms of Euclidean distance. And then you give a weight using cosine similarity as the weights. Okay? You can do that. You can do a number of things. You can use some probabilistic argument, for example. You can use the Euclidean distances as weights, and then compute probabilities over this. So, or actually better, cosine similarity, and then give a sign with probability proportional to the total cosine similarity for each class. Okay, you can do a number of things. And if K is large enough, let's say not very large, let's say an odd number, 5, 7, very often you get very good results. So normally you will pick K to be an odd number so that it is easier to break ties, especially when you apply the majority rule. Okay? But that's essentially the algorithm. It's not much more than this. It's a very easy algorithm. So your training phase is just the points. That's it. Collecting the training points. Your test algorithm is any of these heuristics. Do you want me to make one of these heuristics a bit more precise? I mean, you find them described on the book, but perhaps just one case. For example, I'm just trying to remember. I'm just trying to figure out the notation I want to use. Okay. So let's say the point to classify is X. So X is a document. Okay. And then let's say that I have a training set of points, and I of X let's say this is the set of neighbors in the training set. Then, let's say the score of class C for document X to classify will be just something proportional to this, for example. something like this. Why am I putting the absolute value to get a positive score? Do I need to put the absolute value? Maybe not. Depends on what you want. For example, sometimes your cosine can be negative, but large in absolute value. What does it mean? Well, in that case, the two vectors tend to be almost parallel. They tend to be almost parallel, but but the sign is negative. Is this ever going to happen if I have positive weights? No. If the weights of your vectors are positive, it is never going to happen, right? So in that case, taking the absolute value is immaterial. In other cases, the weights might reflect correlations between documents and terms. For example, a negative weight might mean that the particular term is unlikely to appear in the document because it is not correlated to the document, or to the topic of the document, sorry. In that case, taking the absolute value might be a way of also picking documents that in some sense, I don't know, they might express a negative stance toward the topic. You see what I mean? I don't know, if you do, for example, sentiment analysis, you can have documents that have actually in which terms have positive or negative weights associated, reflecting sentiment towards a given document on a certain topic, okay? So in the cases we are considering now, text classification, all the weights tend to be non-negative numbers. So in that case, you can just take the sum of the cosines, okay? So the inner product will always be non-negative. So actually the angle will be something between 0 and 90 degrees, let's say, okay? This can be a way of weighting. In other cases, you just can compute a score, then compute a probability from the scores. You just take, for every class, the score divided by the sum of the scores, and then you assign the document to one class with probability proportional to the score. Any combination of these heuristics can provide nice results. So, or you take a majority rule, you know? So there are several strategies. So let's try to understand what is depicted in this picture. Let me see if we have another picture. No, we have not another picture. Because they are mentioning Voronoi diagram. Ever heard of Voronoi diagram? Who heard of Voronoi diagram? Or Voronoi tessellation? What is it? So let's try to understand how k nearest neighbor works. Or let's begin with one nearest neighbor. How does it work? So implicitly, for every point in the training set, you can define the subspace of the points. Actually, it is going to be a polytope that will be mapped to this point. You understand what I mean? So given the set of training points, for every point, you have all the points that would be closest to this point. You see what I mean? Yeah? For example, this point was mapped, say, to this point because it happens to fall within the same Voronoi partition of the training space. Okay? So in some sense, the way of classifying in K and N is based on separating not hyperplane, but hypersurfaces. Okay, so this is not a linear classifier. I mean, as simple as it is a non-linear classifier. Okay? So whether or not I belong to a given class does not depend on a separating hyperplane, but actually depends on a separating hypersurface. Okay? So for every point, if for every point you compute it's not a subspace actually, the area, the volume in which all points would be mapped to the given point, you have what is called the Voronoi tessellation. In a surface, if you have a two-dimensional space, it will look something like this. A tessellation will look like a set of polytopes. Okay, polygons actually. They become polytopes in a high-dimensional spaces. And that's called the Voronoi tessellation. So, simple, very simple algorithm. Essentially, no training, almost. So training is implicit. And it is a nonlinear classifier. Wow. You see? Very simple things, but very complex properties. So, when is it going to work? The underlying idea behind K and N is, again, that very often our points, if there is some distinction in topics, this will be reflected. So topics, when I say topics, I mean class. So, for example, the document have different topics. They speak about different things, okay? In that case, this should be reflected in how the documents appear clustered in the space, in the vector space, okay? Now, of course, there is a problem that very often a document does not appear to just one class. I mean, I can talk about, for example, sports and horses at the same time, horse racing, right? That's at the same time about horsing and sports. So very often we humans try to force documents or points into one class, but when they actually belong to more than one class. But still, the underlying idea, we will see how you can have multiple classes, you can handle different classes. But in general, the idea is behind, let's say, distance-based approaches like K-mean, like K&N, is that documents belong to different topics, perhaps more than one topic at once, and this belonging to different classes is reflected in the algebraic structure of the space. Algebraic structure with that I mean that, for example, points corresponding to documents that talk about the same things are clustered together, whereas documents points that correspond to documents about different topics should be, in the average at least, more far apart. Okay? That's the underlying idea. It's always the same idea, contiguity hypothesis. So as I was saying, very often you will not run K and N with K equal 1, because in that case, just a few outliers may ruin your life. You don't want that. Very often you adopt some sort of voting scheme whereby you collect, say, K nearest neighbors, and then you have a sort of a voting. So the different points vote for you to belong to one class. Majority wins or highest score wins, depends, okay? Let's say that this way of proceeding, for example, tends to be a bit more robust than simple majority voting. It's a bit more flexible. So how are you going to implement K and N? Because it's so trivial. In the end, what should I do? I just should take, I should find the K nearest neighbors, right? So let's try to think about, let's be naive for the moment. You have the training set. Let's say that the training set is D. So you have D different documents. I want to compute my K closest neighbors. What should I do? Either Euclidean distance or inner product, which is the same, since we consider unit length vectors. I should compute cardinality of the inner products, right? And then I should find the largest ones. So, one document, linear time. I mean, it's not linear, it's polynomial, come on. But now, it is polynomial, but think of one application. I mean, the training set can be large. I don't know, 10,000 points perhaps. The more the better, right? If you want to return queries at runtime, performing this for every new point is a bit expensive, right? So it's polynomial, it's even linear, but maybe it is a bit too much. Even linear can be too much. Big data, you know? How can we address this? Can you give me 2 ideas on how we can address this?
Find the leader for
Find
the leader for class.
You can find leader. Yeah, one is the leaders. Actually, in our first encounter with k-nearest neighbors was with leaders. You remember? So for a class, you find the leader and you always map to the closest leader. That may work, but actually you're going to miss a lot of the structure of k-nearest neighbors. I mean, it's really very effective because it can define these very sophisticated contours. You know what is the problem? What is the problem of defining leaders? The problem of defining leaders is, let me give you an example. Let me try to give you an example. Okay, I have a very dense cluster here, and I have a more well, let's say my centroid here is somewhere in this point. The centroid here is relatively close, then I give you a point here, or even here actually. We would like to put this point here, but actually we are assigning it there, right? I mean, with classifying and clustering, it's always very easy to find counterexamples, remember. So worst case analysis, if we were to consider worst case analysis, no single method of classification would be fine. We would throw everything away and would say, sorry guys, we cannot do anything. But that's not the truth. So worst case analysis is not the right approach here. So, but anyway, this is one problem you have to deal with. Instead, if you apply nearest neighbors, it accounts for this fact that, let's say, clusters can be across larger surface, a larger portion of volume, for example. How can we preserve this while making the algorithm more efficient? So you can come up with 2 ideas. Our first idea is the following. Very often, if we are dealing with documents, we are, first of all, in a bad case because it's a high-dimensional space. High-dimensional space, I don't know, 10,000 words, terms, or 40,000 terms. Every inner product is a pain. That's the problem. So it's a lot of time. Not just have you to compute inner products with all the other points in the training set, with all the points in the training set, but also each inner product maybe requires an inner product involving potentially 10,000 or more components. That's ugly. This is one first issue. How can we address, so what I was saying, how can we address with this? So we can address with the fact that very often a document will just contain a subset of the terms appearing in the vocabulary, okay? Especially in certain applications. For example, if you want to cluster, if your documents are, I don't know, news posts on news groups, they are very often short messages. It's very hard that they have terms can be a significant fraction of the overall vocabulary, right? So what you can apply in those cases is just ideas that we have already seen from search engines. For example, inverted indices, right? So you build an inverted index for every term with the subset of documents in the training set that contain the given term. Okay? So those are the only, for every term, so when you compute the inner product, for every term you just have to compute a small set of the documents. The inverted index is not going to be as large as the inverted index of a search engine, because typically your training set will be, I don't know, 10,000 documents perhaps. Manually classified, I mean. How many documents can we poor humans classify hand? Can we hand classify? You know, very often, I mean, this training set can be large, but not huge. Okay, so your inverted index will not be very large. It will be in main memory. It will be efficiently accessible. So one idea is using an inverted index. There is another idea, which actually we are not going to see in this course, which is based on approximations. So there are techniques that will actually give you a candidate set of closest points in a time that is considerably less than the number of training points. Okay, how you do that? You use certain classes of hash functions. I'm not going to deal into that. It's called, anyway, if you're interested in what I'm talking about, you can look for locality-sensitive hashing. It's a technique that is not taught in this course, but it can greatly mitigate this problem. K-nearest neighbor search is thought for exactly for this type of queries. Okay? Just to say that very often you apply nearest neighbors, but very often you don't apply it in a plain way. Otherwise, it's not efficient. Normally, it comes up coupled with, let's say, techniques that are intended to speed it up. And we can do this pretty well. Okay? So, let us see what can we say about, let me see how much time I have, actually. So let's see what we can say about K and N in the end. So, no feature selection necessary. What does it mean? Well, it means that actually you are not going to, so sometimes we said you can have, I don't know, terms that do not really add a lot of information, but are there nonetheless. Very often it is pretty robust to the presence of noise terms and so on. So you don't really need any particular effort in this respect. You have no training, essentially. So the training is implicit in the training set. It scales well with the number of classes. What do I mean with the number of classes? I'm not saying you still need those optimizations I was telling you about, but if you think about, the scheme does not change if the number of classes is larger, right? It is the same algorithm. You just will have K documents, and then you have majority voting or something equivalent. On the other hand, you can have what are called ripple effects. You know the ripple effect? Sometimes confused with the butterfly effect. So I change something here and the perturbation propagates. So it can happen if you think about. So it can happen that you change something small here. For example, you add a document from this class a bit closer to the border, and then a lot of things are scrambled. I add a document here from this class, and suddenly the Voronoi diagram in this portion of the space changes completely. Okay? And this could propagate to other classes as well. That's a pain. So there is one issue in this case. If you do it naively, as I was showing you, it will take a lot of time. It can be very expensive computationally. But in most cases, it's more accurate than a naive bias or Rocchio. Okay? So this is a very good algorithm. And as they say, it's Bayes optimal. What does it mean? What does it mean? You machine learners, what does it mean? That it is optimal. Optimal with respect to what? So, so if the world were perfect, we would be able to come up with classifier that makes no mistakes, no classification mistakes, right? But the world is not perfect. So, what happens is that sometimes you're lucky, and actually it is possible to make no mistakes. For example, when you have two classes and they are separable by a hyperplane, in that case there exists one classifier that will make no mistakes. But in other cases, when things are scrambled, maybe there is no way of having no errors. Okay? In that case, what do you try to do? Well, you try to do your best. You try to say, what is the minimum rate of error, the minimum rate of error, so classification inaccuracy, that a classifier will have. Let's assume that this number is, I don't know, 0.1. So it means for this data set, every classifier will at least misclassify 10% of the points. Maybe not always the same if you change the classifier, but at least 10%. How do I prove that? It doesn't matter now. Let's assume that we know that. The next question is, okay, can I build a classifier that achieves this bound, 0.1, 10%? I don't know. That's not an easy problem to solve. But what you can say is that typically, if your minimum rate of error is, let's say, 0.1, k nearest neighbors will do 0.2 at most. In that sense, it's almost optimal. Okay? So twice the minimum possible rate, at most. Which would bring us to another issue, but we will come to this issue next week, not now. In the few minutes that I'm left, I would just like to say, I would just like to comment on what I had promised before, earlier, that is, fine, what should I do when I have more than 2 classes? You promised you would tell us, right? I did promise I would tell you. So, well, what I can do when I have more than 2 classes depends on what I want. Why? So reality is more complex. It is not just that the document belongs to only one class. It may belong to several classes. I mean, in a reasonable way. So it depends on what I want. What do I want from my classifier? Assume that I have k classes now, k. Or let's say m classes, because k is the number, is the parameter of the k nearest neighbors. Let's say that I have m classes, okay? So the type of answer I may want to have from my classifier can be of 2 types. Either I want one class. That is called one-of classifier. So yes, the document can belong to several classes reasonably, but I just want one, which can be the most likely or the most correlated in some sense, the most appropriate for the document. For example, the document can be about horses and sports in several ways, so it's more about horses, or it's more about sports, depending on the language, on the lexicon it contains. So I want to have, let's say, a more representative class for a document, or it can be the type of answer you want is any of. So you want to have a set of classes for which the document is, to which the document is associated, can be associated. How? For example, in terms of relevant score, some relevant score. So in that case, you will have for every document, let's say that you have m classes. Your answer might be a vector for a document. Let's say, let's put D. For a document D, your answer might be a vector of m components in which SD of CI is the score of the class for that document. For example, let's say m equals 3, you may have, I don't know, what do these numbers mean? I don't know, confidence scores, for example. It means that with some decent confidence, the document belongs to the third class, with a medium confidence to the second class, and with very low confidence to the first class. Okay? You can return a vector like this, for example. If you think about it, this is just a labeling of the documents. Let's say a real labeling of the documents. That's any of. Instead, if I wanted one of, in that case, I could have confidence rates for every class, and then I would say, okay, since you want one class, this for me is the more relevant class. Okay? And how do I do this in practice? So we have seen how you can classify documents in two classes. If you have m classes, what you're going to do, one thing that you can do is the following. You consider say you have 4 classes, okay? Or let's say these are 4 classes of documents, 4 potential classes. What you will do, if you have a binary classifier, if you want to have a classifier for 4 classes in this case, you can use just a binary classifier, a linear classifier, for example, or a nonlinear classifier for 2 classes in the following way. You start with C equal C1 and C. Then you run your classifier for this partition of the classes, and for example, you get a score, a confidence score for class 1. Then you run your classifier for this other partition of the classes. And you get a confidence score for this class, and so on. Eventually, you will get one confidence score for every class, and then you apply one of the rules you want. Okay, that's one. Then, depending if you want any of, if you are performing any of classification, you will just return the vector of scores. If you want one of classification, you will get, for example, the highest scoring class for the document. Okay, that's one way in which you can do this. And very often this is the type of heuristic that is used. I still have 5 minutes. You want to ask questions? Any questions? Okay, then I will tell you what is going to happen next. So next Thursday, the other guy is, I don't know, you could do something practical or no? Are you skeptical? I don't know. I asked him explicitly. He said, don't know yet. For sure, what we are going to do at some point, what I would like to do when we are done with all this stuff, is just to, I don't know, spend a couple of hours on just looking how this stuff is implemented, for example, in scikit-learn, and run some tests. I mean, it's easy to do. There is a very nice classification task. You know the 20 newsgroups dataset? You will know it. No, it's very easy because it's just you can download it automatically in scikit-learn, and essentially we can run all these algorithms. They are already implemented and see what they do. I mean, just apply them. It's a real dataset. It's not. It's a real dataset with the ground truth. The classes are already there. You can split the data in training set and test set. We can run 5-fold cross-validation, all the things I was telling you about. So then next time, I would like to tell you a couple of words about this, because you did machine learning, right? Some of you. So some of you have heard of bias and capacity, perhaps, or not. So there is, I mean, in the end, there is a final question I've not answered yet, which is the following. Fine, you have shown me Rocchio. Okay. You have shown me K and N. Fine. You showed me naive Bayes. So at least 3 classifiers that can be used for the same task. So what? Which one should I use? And why would I prefer one over the other, right? If so far it looks like a recipe of magics. A magic recipe. So you know the dragon is attacking and you try all magic formulas that occur to you. But how should I proceed? When is one classifier performing better than the other? Given that showing that one classifier is better than the other requires, in theory, requires a considerable effort and cannot be done in general, still we can understand at least which factors determine whether or not a classifier is going to perform well on a given data set. That is what I would like to do next time. Okay? And it's not really hard to do. And it's useful. I will introduce a couple of notions that have to do with some of the fundamentals of machine learning. I don't know if you saw them. I will not even mention them, but they have to do with notions such as VC dimension or so, or the like. No, I'm not going to torture you with VC dimension. Not at all. No VC dimension, I promise. But still, the things I'm going to tell you are related to these notions, even if I will not mention them at all. Okay? So I guess I'll see you next week. Next Monday, perhaps. Or next, I don't know, depends. We have to agree with the guy. So, okay? But I'll see you next week anyway.